people.
Hello, everyone, and welcome to Grid Interactive Efficient Buildings, Reports from the Field. My name is Carrie Mead. I'm the Executive Director for the Smart Building Center, and I am so lucky that I get to moderate this awesome conversation with Courtney and Tanya, two rock stars from up here in the Northwest. I'm super into this topic, and so I just feel really grateful that they can be here and we can continue the conversation. Okay, so before I share their bios, I wanted to just give a quick intro to what we're going to be discussing today. So for those of you who participated yesterday in some of our sessions, we had a conversation with three utilities, PG&E, Seattle City Light, and Puget Sound Energy, where they discussed grid interactive efficient buildings and demand flexibility from the point of view of the utility. So thinking about the value of demand flexibility for utilities working to integrate distributed energy resources into their supply portfolio and ensure increased reliability for customers. Today's panel, we'll hear from Courtney and Tanya, who are coordinating with serving utilities in the field to work with customers, explaining how GEBs work, the potential value to facility owners and managers, and implementing projects. So the way things will work today, we're going to have a presentation from first Courtney and then from Tanya, and then we will have some Q&A opportunity at the end. I have some prepared questions, but we also do invite all of you to submit questions if they come to mind. We have the chat function enabled so you can interact with one another, but we will not be monitoring it. So if you have any questions for our panel, please submit them through the official kind of Q&A button on the bottom of your Zoom. And if there's time at the end of the discussion, we will get to those questions as well. Okay, so let me first just read the bios of both of our panelists, and then we'll turn it over to you, Courtney. So Courtney Blodgett, did I say that correctly, Courtney? Okay, good. Courtney is the Director of Strategy and a founding member of EDO. She has 20 years of experience working on clean energy, innovation, and sustainability. She was Managing Director of Brooklyn Microgrid, one of the first peer-to-peer energy trading platforms. She led the impact investing team at Vulcan, the family office of Microsoft's co-founder Paul Allen, with a focus on clean tech investments. She was a climate change technical advisor to the United Nations in Rwanda and to the UK government. She has worked on renewable energy and energy efficiency projects and programs around the world. Courtney is on the board of directors for Kilowatts for Humanity. She is also the founder of Yield Positive, a blog about sustainable investing for the everyday investor. So welcome, Courtney. And we also have with us Tanya Barham. Tanya is the CEO of Community Energy Labs, a woman-owned and led energy technology company with a mission to enable affordable decarbonization of community buildings by 2030. CEL's core AI-powered clean building control platform was a regional winner of Clean Tech Open's 2020 International Accelerator, an overall winner in the 2020 Madrona Venture Labs Go Vertical Challenge, a 2021 Impel Plus Building Innovator, EPRI Incubate Energy 2021 cohort member, and 2021 U.S. Department of Energy SBIR awardee. CEL emerged from the nonprofit PECI as a nimble social enterprise with a suite of grid edge and community-centric IT approaches to climate adaptation, local empowerment, and clean energy. CEL's executive team have track records that span 20 years, from startups to organizations as large as Southern California Edison, NASA, and Southern Company. In 2019, while at PECI, the team won the Smart Electric Power Alliance's Visionary of the Year award for developing scalable community approaches to energy projects and technology deployment. Welcome, Tanya. We're so lucky to have Courtney and Tanya both here with us in the Northwest and virtually today in the Smart Buildings Exchange. So just to kick things off, I'm going to turn over the discussion to you, Courtney, where you can share a little more about yourself and whatever else you'd like to talk about today.
Great. Thank you, Carrie. So I'm going to work off of the base that people know the basics of grid interactive efficient buildings, but for anybody who's not familiar, I'm going to try to weave in a little bit of information into my presentation about what that means, just in case you're not familiar with the concept. Mm, we'll get there. All right. I don't know why it's showing my. We did just practice this, everyone, I promise. For some reason, it is not sharing.
We are seeing it.
Oh, you are? Oh,
Mhm.
interesting. Okay. Hmm. So you could see my presentation?
Yep, so I'm seeing the title slide and, yeah, seeing the presentation. It's
Okay.
not in presenter mode necessarily, but I can see the title slide.
Okay.
It's in presenter mode now.
Great. Awesome. Sorry about that, everybody. We're a Teams user, so it's always interesting to get used to a different platform. So today I'm going to talk about the Spokane Connected Communities Project, which is a case study around grid interactive efficient buildings, or GEBs. Horrible acronym, but it is what it is. So first, a little about EDO. So EDO was really formed with this mission of creating GEBs. So we partner with utilities to transform buildings, making the buildings grid interactive to achieve energy efficiency, reliability, and decarbonization. So this photo that you see here on the right is kind of the origin of EDO. And so this is the South Landing Eco District, which is located in Spokane. This land was slated to be an Avista substation. And instead of building a substation, Avista, which is the utility in Eastern Washington and Northern Idaho, partnered with McKinstry, which is a commercial building mechanical, electrical service provider, and said, why don't we try to create a campus that is both highly efficient and which can be a proactive part of the grid? So instead of just consuming energy, we want a campus that can respond to the grid needs. So the South Landing Eco District was built, and it is highly efficient, and it has an energy use intensity of less than half of a standard commercial building, and a suite of DERs, including solar, storage, both electrical and thermal, heat pumps, all sorts of different DERs that make this campus something that can respond and reduce load when there is a peak happening on a Vista's grid. So this South End Eco District was so successful that two companies said, let's form a startup that really focuses on scaling this idea of grid interactive efficient buildings for commercial buildings. So the Spokane Connected Communities Project is a Department of Energy funded project that is a non-wires alternative for a substation. So the substation is located in Spokane. It's a Third and Hatch substation, and it is nearing capacity. So instead of upgrading the substation, the aim of the project is, can we defer or prevent the need to upgrade the substation by reducing load on the substation? So the project aims to reduce grid congestion by creating 1 to 2.25 megawatts of dispatchable and flexible load to save customers up to 900 megawatt hours per year from energy efficiency measures and reduce CO2 equivalent emissions by 325 tons per year. So that map you see on the right, that's the region where the project is focused. It includes a university district, a number of low-income housing facilities, community centers, a wide variety of customer types. So this is the pilot area where we are focusing this kind of GEBs project. And our partners in it include Avista, Urbanova, which is a local nonprofit, and Pacific Northwest National Lab. So what we're trying to do with this project is kind of go greater than just the building. So we're doing aggregation of buildings, and that is the non-wires alternative, but we want to look at everything holistically. How do we create GEBs in a targeted and thoughtful way? And so to do that, we first started with a substation peak load analysis. So we looked at the electricity use from Third and Hatch substation, and we analyzed it over the course of a couple of years to understand what the drivers were of peak load. So for those of us in the Pacific Northwest, I think we all remember the 2021 heat dome. And there you can see this real spike on a Vista system. For the first time, they had major outages, and there was outages for more than 4 days in parts of Spokane. And then the 2022 heat wave, you can also see that spike. So Third and Hatch substation has a peak of about 62 megawatts during heat waves, with the peak period during the day being between 1 and 4 p.m. We also found that the top 100 electricity users were causing 42% of the coincident peak. So that's really important to think about when we're trying to design a program that is focused on reducing load and shifting and shedding load. I think the other thing that we need to layer on top of this, though, is equity. So how do we bear in mind that 100 of the 11,000 plus users are driving almost half of the peak? But then we want to make sure that this program is helping everybody in the community, particularly low and medium income residents. So that's something that we really have to be thoughtful about as we're designing the program. So we then moved down to the next level. We looked at the feeders in the substation. So again, we looked at the heat dome event, and we saw that on 2 of the feeders, it was mainly commercial and industrial customers that were driving the peaks. And that is the blue and orange. Sorry, it's a little bit hard to see. So blue and orange customers are C&I. And then 3 of the feeders, the peaks were being driven by residential. So that is red and green. And then small and medium businesses contributed on all feeders. So once we had the data in place, then we really wanted to put customers at the forefront of the design. We can design a program that, that speaks to the data, but if the customers aren't interested and engaged, it will never be a success. So we moved on to doing a customer survey. So we surveyed 2,200 resident and 500 C&I customers. We did postcards with a link, paper surveys, phone call follow-ups for commercial customers. We got responses from 130 residential and then 14 small and medium businesses. And one of the core questions we asked was, how would you feel about participating in a smart thermostat program that will allow the utility company to adjust your thermostat a couple of degrees during high times of use in return for a rebate or discount on your energy bill? More than 65% of respondents said they would be interested in allowing temperature adjustments. Those bars you can see on the side of the screen are for the different feeders, and the shades of green were yes, we will allow adjustment to our thermostat, which was really encouraging because you never know how customers are going to feel about that. So then we took that information, and you can see that this is quite the process. And I think something that Tanya knows well, GEBs are not easy. There's a lot of different pieces you need to take into consideration when you are working with buildings with different customer types, with really trying to figure out how to shed and shift load in a way that is useful for the grid. And so in this project, we're pretty lucky because it's a grant funded project, so allows us to be creative. And so we worked on creating solution packages that kind of spoke to the needs both of the grid and the customer. So we had to balance, how do we customize offerings for all of the different customer types that we're working with, and cost, because there is a limited amount of funding available. And we want this to be something that's replicable. So we don't want to use just the most expensive technology, even if that would give us the most flexible load, because we want Avista to scale this program. We want other utilities to be able to look at this program and say, yes, I could create these types of packages as well. So we wanted to leverage existing utility programs, particularly energy efficiency programs, and then vet the packages based on the customer feedback and the quantified demand flexibility potential. So that graphic is, we were doing calculations around what is the baseline during an event, and then how much load can we drop during the event if we call on these different packages. So these are the packages that we ended up with. And some of the customers received different kind of configurations of these technologies. But for residential, we ended up going with weatherization, bearing in mind those energy efficiency targets and that we want to kind of reduce the overall energy cost, particularly for low-income customers. Smart thermostats, so we partner with Ecobee and smart thermostats, dual fuel heat pumps, and then battery storage for some of the customers. For small and medium businesses, we went with smart thermostats and rooftop unit control and some additional sensors. For a large commercial, we integrated with the building automation system to do optimization of the HVAC system, so shifting and shedding load in advance of an event, and then some additional sensors as well. And then for the community centers in the program, we did EV charging, PV, and battery storage. So one thing to think about when we're working on GEBs is like, what is the regulatory framework that is in place that allows the utility to offer GEB programs? And the regulatory framework is really different between every state utility. It's different for municipalities. And so it as a solution provider, you're trying to work within and often evolve existing regulatory frameworks around demand flexibility. Because it is relatively new, there are regulatory frameworks in a lot of places for demand response, but what we're trying to do goes beyond just demand response in a few events a year. We're trying to integrate energy efficiency. We're trying to have load shift and shed be more dynamic. So not 8 times a year, but load that can be moved on a more regular basis so we don't have to upgrade that substation. So Edo collaborated with Avista to receive approval from the Washington UTC for the tariffs and incentives that were part of this pilot. So I'm not going to go into all the different incentives because there are a lot of them based on the package combinations. I think the incentives for residential and small and medium business is something that's pretty familiar to a lot of people who might be participating in smart thermostat programs. It's up to $50 a month with a bonus for not opting out. Um, and then for residential packages that include smart thermostat, weatherization, and heat pump, it has that same smart thermostat incentive. But then as part of the pilot, Avista will be providing at no cost to the customer the heat pumps and weatherization. And then for energy storage, it's a one-time incentive of $400 per kilowatt and an annual incentive of $15 per kilowatt per participating in events. And then finally, for commercial and industrial, there is a $50 per kilowatt year capacity payments and 20 cents kilowatt hour performance payments. And that capacity and performance payments is something that you see in a number of different utility territories and states throughout the countries. That price varies depending on where you are in the US. But that is what we're seeing more and more of as we see the growth, at least of more standard demand response programs. And then recruitment. So, we've done all of this work to try to make sure that the pilot is designed in a way that encourages the participation of customers. And thankfully, we are finding that. So we're mainly recruiting commercial customers at this point in time. And you can see there's a wide variety of customer types that are interested in participating. So everything from schools to boat marine supply retail companies and fitness centers and your tattoo parlor down the street. And that's really exciting for us because we want a wide variety of building uses, particularly for this pilot where we have a little extra wiggle room to try things out. And just to read some of the kind of feedback we're receiving from customers. So one of the school district facility managers said, I geek out on energy information. I have so little of it. I've been waiting for someone to offer me an energy management solution. Small business owners want to know when batteries will be part of the program for them. And this is something, as in the Pacific Northwest, we're starting to see, similar to California, some of the plans being put in place for shutdowns when there's a high risk of wildfires. And so these customers are thinking from a resilience point of view. And then another small business owner just saying, we're excited to have a solution to help us manage our energy bills. And the bill credit from participation is kind of an added bonus. And that's something that is pretty unique to GEBs, is that there is this value stacking for customers. We're not just saying we'll give you a bill credit 8 times a year during an event. We're saying we'll help you manage your energy consumption, reduce it overall, and then bring the demand flexibility piece on top of that energy efficiency. So just in conclusion, a deeper understanding what is driving load allows utilities to address peaks in a targeted manner. Comprehensive solution packages provide customers with multiple value streams, encouraging them to participate, and equally important, encouraging them to not opt out once they're participating. That is a challenge for some demand response programs, is that customers just get tired of having their thermostats controlled. But here they're seeing that constant energy savings coupled with the demand response payment. So it is that value stacking that we think is really important for customers. Regulatory frameworks need adjusting all over the country to allow for good interactive, efficient building programs. And then happily, with sufficient incentives, customers are ready to engage. So thank you very much. And I will now hand the screen over to Tanya. Or Carrie, I'll stop and see if there are any specific questions.
Yes, well, there are. There was one that came in that you answered regard to the cost, what do the customers pay versus the utilities. There are several other questions here that I don't think we'll have time to get to all of them right now, but perhaps at the end. But I did want to give one question a moment just because you might be able to deal with it quickly. How did you deal with apartment dwellers? Many landlords are at best indifferent and not interested in installing smart thermometers or even thermometer-enabled heating and cooling equipment. I would think this is critical for lower income individuals.
Yeah, great question. I mean, I think this is one of the kind of age-old questions of energy efficiency as well, in buildings, is how do you deal with the tenant and landlord situation? Multifamily is part of the program. And I think what we're doing there is we're trying to work with both the tenants and the landlords to bring them into the program to understand the benefits so that we can share the cost savings with kind of both sides of the lease.
Okay, and I'm actually going to give you one more clarifying question, kind of interesting. Doesn't paying for heat pumps add AC to homes that would exacerbate the peak load issues during heat domes, even if the thermostat is controlled?
Yeah, great question. And definitely something we need to think about. But I think some situation the buildings already have air conditioners, so we're replacing them. I think the other thing is, at least here in Seattle, no, I think we used to be the largest city that was under air conditioned in the country, that had very limited air conditioning. And yet we're seeing this real dramatic growth in air conditioning as we're having more of these extreme heat events. So I think assuming that people are not going to buy air conditioning is probably no longer a valid assumption. I think there are so many of these extreme heat events, and Spokane is relatively hot. And so I think more and more people will be buying air conditioners, whether there's a program or not. So if we can incentivize them to instead install an efficient heat pump, that that
Plus
is
the heat pump
overall better.
addresses their heating and their cooling.
Yeah.
So it's a twofer, as people are adding that cooling anyway, do you want to have, like what happened in California with the wildfires was, they have this whole air quality permitting issue, especially for the valley where air is very dirty. You've got really bad air quality problems, high degree of asthma and health impacts on individuals who are mostly subsistence living, poverty, higher degrees of poverty. Well, the wildfires happened, and then the sale of diesel gensets and the number of applications for gensets went up. Because if you're not, if you're trying to bury your head in the sand and say, let's not do cooling, you're ignoring what's happening, which is that if people are going to be without power, and there are going to be massive outages due to wildfires, where they're going to go out and get a genset. So I agree with so much wholeheartedly about just saying, all right, well, let's give people multiple pathways. This is heating and cooling. Let's introduce a controllable aspect, an incentive for them to be a better user of that resource, and see if we can harness some value and then share that value with the customer. I think that's so critical.
Yeah.
Yeah, great point. And I keep doing this to you, Courtney, but one more clarifying question that seems like a clarifying question to me. How many residential and commercial customer or users choose to opt out of the programs? Just trying to understand the reliability level.
To opt out of an event or out of the program itself? Well, I can just answer. We probably don't know. So it's a recruitment process in terms of the program. So it's more customers have to opt in to join the program to start. And then we have not yet implemented any events, so we don't know the opt-out rate. But what we're trying to do is like all of this technology we're implementing, that an event should have minimal impact on a tenant, which is different than what you see in some of the large scale demand response commercial providers. They go in and turn off part of a building, or for a factory, they'll say, send everybody home. What a core part of grid interactive efficient buildings is that when you're shifting load, you really are maintaining comfort for the tenant.
Great. Awesome. Okay, I'm going to stop looking at that Q&A box and shift over to Tanya. And it's going to be your turn now to share your screen and talk about the work that
Okay.
you've done in the field.
Fantastic. Well, thank you, Courtney, for really introducing a lot of the. You saved me a lot of time in doing the introduction, so appreciate that.
And Tanya, there was a request for you to turn up your volume. You sound okay to me, but someone has asked if you could possibly do that.
I don't know how I would
Okay.
turn up the volume on my microphone, other than getting into my Zoom settings. Hopefully others can hear me okay. And I apologize. Whoever you are out there, thank you. You're the first person in my whole life who has said that I need to talk louder. Usually it's the opposite. My name's Tanya Behrman. I think where Courtney left off was a great place for me to start. I'm not going to rehash part of what she said about sort of pricing mechanisms, et cetera. And I'm kind of glad that this is what I chose to talk about. There's so many different avenues that we could discuss. Creating the right incentives for customers and utilities to share the value. Creating the right delivery mechanisms so that, like Courtney said, customers don't feel like a utility is reaching in and sort of grabbing their technologies. And then last but not least, I want to focus on the thing that really right now is an implementation issue, and we need more implementers here. It's that issue of comfort. So I've come from utilities. My background was in utilities. And several years ago, I transitioned into this, the customer side of what we called demand response at the time. But I think we're gaining a more sophisticated understanding. And to speak to one of the Q&A comments that came up earlier, what I saw on the utility side was that our demand response was notoriously unreliable. We thought we had 70 megawatts of demand response, but we'd call it, and sometimes 30 megawatts would show up, and sometimes more, sometimes less. And, it's not like a coal fire plant where you call for capacity and boom, it's online, or you've got your spinning reserves if something goes horribly wrong. So, it really created friction between the people that were doing these programs and wanted to engage our customers on the load side, sort of, making flexibility the new energy efficiency, and the people who needed reliable that were responsible for the reliability of the grid in our power operations department. So, I started digging a lot deeper into why and asking our customer, hey, do you participate in peak time rewards, yada, yada, yada. For most customers, even commercial customers, there are industrial processes, there are, that can be turned on and off, rock chippers, heat treatment, other sort of industrial applications that can be shifted. I know a lot of people are looking at agricultural areas, at pumps. People are looking at vehicle charging. There are all sorts of interesting opportunities for shifting, but I got very curious about one in particular that drives so much energy, and that's HVAC. So HVAC generates 15% of global carbon emissions. That's projected to quintuple as, you guessed it, as the globe warms, there's more demand for air conditioning. So, cooling, there's this latent demand, which is only exacerbated, which then only exacerbates the problem. I also started finding, as I started talking to several of our customers, that HVAC not only was the biggest driver of their energy consumption, typically making up 40 to 60% of their total energy consumption, but it also generated about 80% in some cases of their peak demand if they had electrified heating and cooling, or cooling. And those demand charges for mid-sized and above commercial customers could really be a significant portion of the bill. And things were getting more complicated, not less complicated. So you're looking at this map here. What you're seeing are primarily about, I think, 135 sites. Well, there's 125 just in California. So maybe we're up to like 150, 160 sites that have all registered, to Courtney's point, interest in reducing their energy bills, reducing the impact, but on their demand charges. In many cases, we work with K through 12 schools. So for most of our customers or prospective customers who are on this wait list, they're eager to try this technology because it doesn't require a big capital improvement. It works with existing thermostats and sensors, and it works a little bit the way that you might anticipate a Nest thermostat would work. So a Nest thermostat automatically tries to manage energy and comfort, but it does so using statistical models. And those statistical models do not translate well at all to complex buildings, because they're more or less just using a probability to say, I'm going to guess that you're going to want to do this because that's what you usually do. That's fine if you've just got one zone, but as a building gets more complex, as the HVAC gets more complex, how do you both guarantee comfort and save energy when the building itself has very complex physics? The thermal characteristics of that building will be influenced by, one side of the building might be hotter because it's south facing. There might be different types of composition. One might be a second floor, one might be a first floor, one might be southeast, one might be northwest. So these buildings are too complex for AI that's based only on, probabilistic models to translate well. So our innovation was to commercialize a breakthrough machine learning technology that actually takes a low order physics model. So it starts with just a physics model, a really simple physics model. And then it uses sensors in the building to update that physics model. So, and everyone's like, well, where are those sensors? And I'm like, a little something called a thermostat. It's just measuring that indoor air temperature using weather APIs, using solar APIs. And then occasionally we'll also install meters, electricity meters. So very quick, simple install, an integration process with the building automation system or the smart thermostat. In some cases, an actual installation of sensors like a meter, or adding a data-rich controllable thermostat. And the cool part was in 2023, I think it was last year, we did publish a few. I'm going to be putting my link. I have an ulterior motive today, by the way, which is that we are actually in the process of hiring folks, and I'm going to describe to you the problem that you can help us solve if you come work for us. So when I put that link there, you can also go to our projects page and read the data that we published in the Journal of Energy and Buildings in 2023. That was from our early pilots of the technology in the field. I think that was 2 climate zones, a total of 3 buildings, a total of something like, I want to say 10 rooftop units and heat pumps. Now we have a new study that'll be coming out with hundreds of buildings and hundreds of RTUs, et cetera. So more to come. So the cool part is, yay, this algorithm works. It's able to reduce peak demand from HVAC in heating and cooling seasons by anywhere from 11 to 30%. So that peakiness. It's also able to reduce overall energy consumption, depending on the shell of the building, depending on other attributes of the operation of the building, anywhere from 3 up to, in some cases, close to 20%. That's very rare. It'd be closer to 10 on average. So it has an energy efficiency overall, and it has a peak demand reduction attribute while maintaining optimal comfort. But it is a very different way. It's using this data to make these decisions, and it's making these controls autonomously. So no one is shifting schedules, no one is building rules. You basically have a little virtual engineer who sits there looking at every RTU every 5 minutes in every room, predicting what the indoor air temperature will be and saying, can I just let it ride? Can I do my cruise control, or do I need to heat and cool? And what's going to happen to the price? So 7 of these campuses, and I don't know what percentage of the RTUs and buildings that is, we're also on a real-time price that changed every 5 minutes. And we'll be expanding that pilot from just in SCE territory, Southern California Edison, to PG&E territory as well next year. So, that's the cool news, right? It works, it has potential. The bad news is the devil's always in the details. And as we move toward making flexible demand a really predictable form of flexibility for the grid, sort of the new energy efficiency, that does require making sure that we're maintaining comfort at the same time for our customers. And then it doesn't require necessarily huge capital expenditures up front. But there are several things to keep in mind as we work toward a solution. And I'm going to go over with you some data. This is in a slide deck that actually says confidential on it, but I'm showing you the slides that are less confidential. And I want to talk to you from a really granular perspective so that you get a sense of some of what still needs to mature as we get this technology to a scale where, we're not just adding, okay, we've got 160 people waiting to try the technology and we're doing 30 a year. We want to be able to add all 200 of those customers to this system at the same time and really scale this technology. So I want to talk a little bit today about sort of commercializing these automated service provision technologies. And it does have a lot of stakeholders. It has customers involved, it has utilities, it has regulators, but I'm not going to rehash what Courtney already covered so eloquently. So let's talk about what the solution entails. So again, I'm going to come down to the granular area. I hope we've already convinced you that this is a cool and compelling way to engage customers in, I don't want to call it a replacement for energy efficiency, but a both and, like buildings that can be both use as little energy as possible, and at sometimes in the day be able to flex their energy or even use more in order to make use of intermittent renewables. Well, in order to do that, we need a lot of data. So data governance becomes a really huge part. And again, stakeholder management in the specification and design of AI ML type systems. So in our product, typically, you have the physical building or the physical structure. And you also have the sort of representation of that building within an organization. So there are the people structures, and I like to call that the topology of relationships. And then we have digital infrastructure, so the topology of their networks as a way to be able to move information around, and the physical topology of their building. And building data is very hierarchical. So there are lots of relationships between various aspects of this building that, again, because the physics in commercial buildings are so complex, you can't be deaf, dumb, and blind to those. Statistics alone would not allow you to issue those control decisions as rapidly as necessary in order to keep people comfortable if you just tried to use raw data alone. Too complex. So in order to create this basic physics model and then update it using telemetry, there are certain things that we need to gather. And I'll go a little bit deeper into those. We need to gather some metadata about the building that implements the parameter guesses on the early physical model. The model basically becomes the brain for our virtual engineer or the machine learning. The machine learning then needs to pull in some real-time data and make some little changes to the building and see what happens. And it then updates its model like, oh, I get it now. Oh, okay. My guess is that this room is, like so. When I make this change, I watch what happens over time, and I'm like, oh, I actually now have a much better idea of the thermal transfer. We call that the training period. At the end of the training period, if we can see that the virtual engineer has used its model to good effect and adapted its controls such that it can adapted its understanding, sorry, not its controls yet, such that it can accurately predict in shadow mode with 90% accuracy the indoor air temperature of every room in the building that it's going to control. Then we say, have at it. You get to be at the controls now because you know what's going to happen and you know it accurately. So we trust you to make good decisions. So some of the things that it needs to look at, obviously we need metadata about the building, but the telemetry that it needs is going to be energy data, of course, the consumption data from the devices that we're hoping to control, and so that we can see the impact on at least one representative type device. And then it's also going to need, especially when we're participating in a real-time pricing program for utility, it's going to need to know the overall campus consumption, the consumption of individual buildings, and then how much contribution each unit, each HVAC unit, whether that's a VAV system or an RTU heat pump system, it's going to need to be able to estimate how much of that overall energy demand at the building level and the campus level are thanks to changes that it is making at, let's say, 100 RTUs throughout the campus. So in order to do this, it lives on a cloud. So this could be, for any of you, it could be Google Cloud Platform, could be Azure, could be AWS, using stuff that you're very familiar with, I'm sure, like EC2 instances, Lambdas, et cetera, and has a number of software services. It needs to do basically two things. It needs to access enough devices to update its physical model and physics model of the building. And it typically is going to do that in two ways. One, it can communicate through a cloud API, which many of you are familiar with. And then the other is it will need to be on a local network through a local API, talking to a building automation system or using a protocol like BACnet over IP. And it's really just trying to do two things. It's collecting data to update its model, and it's sending a control signal, but it is not sending controls to the embedded controllers on those devices. It is only sending set points. And it's a little bit like, I'm trying to find a good metaphor for this because this really blows people's mind. It's not a rules-based control. It's not like putting a PID controller on a system. Those set points aren't really used as set points. It just knows what's going to happen when it gives you this set point. It knows what types of physical changes it will effectuate and how that will impact the whole campus's energy consumption and how that will impact the individual comfort of that zone based on where that zone is in the building. So it's really just a lightweight way for it to do this. And I think I'm like, how do I communicate what's happening here? It's a little bit how like when we first started using Waze and Google, you would be like, wait, why are you sending me down this weird street? Because somehow in the algorithm, it's like, I know that you're going to get to your endpoint faster if you go this way that you have not always gone, or I know that there's traffic somewhere else. So it doesn't use set points the way that we think of set points. It uses set points to effectuate some change that it know will get you the outcome you want, which is a comfortable room at, 30% lower peak and 5 to 20% less energy use over a period of time. Okay, I'm going to move on. So, this, like I said, in data governance, we really have to think about like, who are we building this technology for? And who uses this data? How do we gather this data? And what does that data solve? And this can be quite challenging because obviously our customers are customers. These are the buyers and facility managers who, they're trying to understand what's happening. They want to know if the robot can help them reduce their bills. And they sure as heck don't want to be spending 5 hours a week futzing with thermostats, futzing with schedules, listening to people complain that every time they try to save energy, it's too hot, it's too cold. So ultimately, those are our customers. It is true. And then we also have internal customers that use this data and use our system in order to help the robot learn. However, at the end of the day, we've really decided that in our first pass, at least, the robot is actually the customer. It is the customer's employee. It is the virtual engineer. It is the one that needs to do the work so that the customer does not. And so what that means is that we have robots that have different strategies. So just like in the course of a day, you might have heating mode, you might have cooling mode, you might have auto mode, and you use these different modes, unoccupied, occupied mode, during the course of a day in order to effectuate certain changes. Different robots have different strategies. And so for each strategy, it's very important to know what types of data that robot needs in order to do their job effectively and to basically allow our customer to receive the benefits that they want without needing to pay attention. Our robot has done a good job if nobody complains and nobody knows that it's there until they save the money. So, but in order to do that, we need customer and company data so that, again, we understand the topology of the relationships from the customer. And we need data that enables the control. And here's where things get a little messy in the world of GEBs. We have two really important types of data. So this is our data structure or hierarchy. This is not going to look different than what many of you, if you're a data-driven company, you've got to have a way of thinking about the world that you can digitize. So, we're looking at organizations. Of course, we're going to get telemetry or, time series data that we need for the robot, documents, contacts, events, etc. But there's this whole area of data here in green that represents the physical building that you need to create a digital twin. And that in the past, if you want to build a model, requires 400 parameters or calculated parameters. It requires days and days of collecting audit information and needs to be organized and defined in a way that can be usable by the robot. And that is, there's a great schema. Some of you might be familiar with BRIC. That is used to represent that data. It's evolving, that data in controls. Really narrowing down what is critical in order to effectuate control was a years-long process for us. And I want to talk to you about a couple other implementation things when we think about data governance. And when you're out there thinking about managing these types of, grid interactive buildings, before we get to control, we really want to think about, like, how do we identify the critical people and the critical data and interface points in order to allow that engineer to do the work and really take that burden off your hands. And it will take that burden off your hands and do it. It's let the robot do it. It's cheap, it's effortless, but it has to have good information. Otherwise, it's garbage in, garbage out. So the things that we're looking at typically here are like buildings, floors, zones, spaces. Things like variables are going to be the construction type of the building, the window to wall ratio, stuff you can get off of Google Maps or drawings that someone provides. But then we're also going to be looking at attributes of your HVAC equipment itself, which of course we can get from the manufacturer's book. But what we see with a lot of customers is they might have drawing sets that are 80 years old. So we need quick ways to go in and collect that metadata that helps determine what the physics of the building might be in a very quick way. So where the traditional ASHRAE level 2 audit might take multiple days, when we go in to do an audit, it takes 2 to 4 hours, regardless of the size of the building. So we can do a large secondary school campus that's as big as a small city, it feels like, in about 4 hours, because we're really looking for very specific attributes that we can use to spin up that physics model very quickly. Now, how do we get that stuff? This is the fun part. And we've learned a lot along the way. And I'm pretty much at time here, but I'll whiz through these very quickly. So the things that we learned along the way is that we can integrate with devices and external services in order to get the data. But in order to do that, we need to have a good understanding of the customer's network topology and security up front. So our customer needs to connect us with IT, connect us with their controls vendor so that we can talk to them really quickly and be like, hey, where is everything? How do we identify it? How do we get it? And then making sure that our internal services that are serving up, taking some of this data, warehousing it, and sending back out are reliable, and really building those for scale and asking sort of, why are we using this piece of data? and how do we build it for stability? And so what we found is that we were only using integration with external devices about 20% of the time, because everybody thinks like, oh my God, more integrations, it's going to be so hard. But what we found was that we were underutilizing these sources of data, and we should have been spending closer to half of our budget for collection of data through things like a BAS system, through talking to a thermostat, through installing a meter and talking to the meter. What we found was that when users provide information, it's not always accurate. And within our company, people weren't always putting it into the same data store. So creating an ontology that we all could use as a team became critical, and really simplifying it so that it was much easier for people to navigate their way around. And then last but not least, we were spending a lot of time having our data scientists really train the robots. But the deal is that a lot of this could be configured through software in a way that we didn't need to do manual training and parameter tuning, and we didn't need to do it at the level of granularity and detail. So knowing when it's okay to zoom up and how these relationships work with the physics of the building was really critical for us. So that I hope this wasn't too boring for the people on this call, but I really believe that as an ML and data company, it's really important for people to understand why we make certain requests up front in order to get to that result that we all want, which is a completely hands-off control.
Well, I loved it. Thank you, Tanya. I do want to address a clarifying question from the audience. How do you deal with humidity?
That's a great question. So again, we don't necessarily mess with the embedded controls. We really are just looking at set points. So if there is already logic in their heating and cooling modes for their thermostat, or in their building automation system dealing with humidity, we're not going to change that. So the only point that we're looking at is really just the set point. And really, the reason we're using the set point is to just get the compressors to run or not run. We are experimenting with a new algorithm right now that also looks at damper position and economizers. But right now we're talking about pretty simple systems, RTUs and heat pumps. We do have a model for VRFs that we've looked at, but VRFs and VAV systems with damper position or integrating economizers is our next step.
Okay, awesome. Well, you did a great job taking something super complicated and really explaining. It's so complicated. Okay, so Courtney, if you want to, there you are. So we're going to dive into some questions that we put together for the panel, and feel free to continue to submit your questions as well. And we will get to those as we're able to. So for the first question I have for both of you, and I'm going to start with you, Courtney, and then you can answer, Tanya. Both of you kind of touched on this, but if you could elaborate a little more on how field implementers are developing load packages, or something perhaps unique to occupancy types that offer sufficient value for the utility and minimal disruption for the customer. So Courtney, you spent some time talking about this, and Tanya, you also touched on the idea that buildings are very unique from each other. So can you just elaborate a little more, Courtney, and then Tanya?
Yeah, so I think the packages I described in Connected Communities are pretty unique. It is a grant-funded pilot, and so there's a lot of extra room to look at different technologies and then use some grant funding to help subsidize those technologies. But what we're seeing in some other territories, for instance, we're working with Eversource on a project in Connecticut. And they have existing demand response program and existing energy efficiency programs, but nothing is kind of offered holistically to the customer. So what we're doing is we're working with the incentives that are already improved by the regulators in Connecticut, and then whatever is existing in the building where we can flex load, and we're then packaging that as one thing for the customer, just to improve the customer experience. Similar to Tanya's work, most of what we do is around HVAC controls, and we can work with any existing DERs if there are any, but at least in commercial buildings, you're not yet seeing that many. But I think as we have more questions with reliability, we will begin to see more batteries, and EDO can optimize anything that's behind the meter. So any existing DERs.
Yeah, I'm chatting with someone here in the Q&A. Hopefully I didn't not too many spelling errors and not too terrible of an answer. Can you repeat the question? Because I got distracted by the Q&A.
Yeah, no problem. I know the virtual world, right?
Yeah.
So really, we're just talking about to what extent field implementers are, developing
Got it.
flexible packages. Yeah.
Yeah. This is a work in progress. To what Courtney said, we're working in a lot of different contexts. So we do have a number of just research and development on the core ASP technology, but there are multiple aspects to this, right? There's the price and the price signal aspect of it. So we've experimented in the field now with 3 different types of prices. In Oregon and Washington, we're seeing a flat rate plus demand charge, and the demand charge ratchets are pretty basic. So these are your typical, anyone here who's from a PUD in Washington or Oregon, you're going to recognize these rates. And really the customer is just looking to reduce their overall consumption and or their demand charges if they're in that, over 50 kW, over 100 kW bracket. Now, we also worked with what we're seeing increasingly are these time of use rates that shift a lot. And then that's also changing as NEM changes, as the cost of batteries change, the compensation that people are getting for their solar production. It's just become like obscenely complex for customers. And then the third type that we're working with is a dynamic price. The one that we've experimented with so far is a transactive price, which it's a lot. It takes the fixed cost for the utility. It takes their wholesale costs from that they're trading on in the market, like CAISO in this case. And then it takes distribution capacity, much like I know they're doing in Spokane, and it layers it all into one price that changes every 5 minutes. They create a subscription for the customer. You buy the subscription, and then just like your subscription plan with your cell phone provider, anytime the customer is at risk of using more than or less than their subscription, in this first implementation, we were able to buy or sell back power. And we found that in every single case, we were able to save about the same amount. However, when the price gets expensive and how much ability that customer has to flex at that time and the volume of cost are all things that need to be considered in the beginning. So, we work primarily with schools. If you're a high school, there's going to be value there. You've got this huge load. You've got people there at night, even middle schools, you still have activity. But in a lot of these places where the peak is happening in the evening, an elementary school might not be the best value. So I think less than having sort of a value package, there's an understanding that there's a grouping of customers and what types of products are a good fit for that customer based on their load shape and based on the shape of the price that they're interacting with. So that's what we spend a lot of time on the upfront is like, hey, if we can figure out what your energy usage patterns are roughly going to look like based on your occupancy patterns, and we can look at what tariff you're on, we can tell you whether or not it's going to be a good fit for you. And it really has to be sort of based on their tariff and their occupancy patterns and whether those two things are going to bing, 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 create a match. Now, that being said, I don't think a lot of the prices, the utilities themselves are having a difficult time understanding how to rapidly iterate on these tariffs and not piss everybody off at the regulatory commission meetings. So it's a really painful process. And one thing that we learned with the dynamic rate program is that if the measurement and verification protocol isn't set up well from the beginning, and sometimes it's hard to know what you don't know, it can be difficult to show the impact or to know where the leverage would be. So we had to be in constant communication with the utility and the M&V, the third-party measurement and verification verifier, to sort of discuss with them like, hey, we were able to transact, we were able to receive the price, we did see a shift, but like the ramp was not steep enough to induce a response from the customer. Like if the choice was between paying $5 more and being hot, $5 more wasn't a big enough difference in the price for them to want to sacrifice comfort. So we think like trying to help communicate to the utility where they have levers in terms of getting that result they want, it just takes time to see it happen in practice, get that information back. So maybe that wasn't a good answer to your question, but.
No, it was a good answer. And I'm going to actually jump to a different question in my pre-prepared questions that kind of builds off of what you were just talking about there. And we'll start with you this time, Tanya, and then go to you, Courtney. But so this is kind of, I would say this is maybe one of the $1 million questions in GEBs, but how are field implementers convincing customers that there is something in this for them? Is it the incentives? Is it the rate structures? If it's the latter, how is the counterfactual constructed? How are they mitigating customer risk for being involved? So you were kind of just chatting about that a little bit there, Tanya, and you can answer first, and then we'll go to you, Courtney.
Well, I think as you saw, we're in a couple states that have pretty intense. California, I think, has 43% higher utility rates than most places in the country. They're changing very rapidly. They have a lot of grid reliability issues, as we all know, places like California and Texas. And so it doesn't take a lot of convincing. The customers know they have a problem, and like they don't have the sophistication or the ability to quickly manage all the complexity of their utility prices. And a battery might not be in the cards, a big capital project might not be in the cards. And a lot of times what we've seen is, again, you pay for this big battery and they're like, oh, this battery and solar is going to solve your demand charge problem or your demand problem. And it's like the logic on the battery is making it so that it's actually starting to charge when there's a lot more solar production, which is the same time in the morning that your HVAC is coming online too. And so it can actually, we've seen some implementations with pretty smart battery companies where they're actually making the demand worse, probably based on interaction with some weird price. So I think the important thing to keep in mind here is that the customers already have a problem. The problem is our customers, at least K through 12, have energy as their second highest cost after labor. And it's already too complicated to manage. Most of them have declining enrollment, so they don't have a building engineer, and they're not going to have somebody who's going to manage what actually is going to take more time to manage, even if you don't have automation. So for them, easy sell. We just need the technology that can actually deliver the comfort and respond to the price. And so the price has to induce the response, and the technology needs to be able to effectuate that response without making people uncomfortable. And the devil is in the details on both of those. I think Courtney talked a lot about, the price and the regulatory things that need to be done to make sure that the price is sending the right signal and rewarding the customer enough. And the technology, as I sort of pointed out, the devil's in the details, needs to work. It needs to have the right data to actually do the thing. So I think that for me is our customers want it. There's no, and Courtney had a long list of people who want it. They get it. It's just working out some of the kinks to make it more frictionless.
Yeah, and I would just add, we mentioned this briefly, but the energy efficiency and improved operations piece of it is really what the customers care about. For them, demand response, if you're able, or demand flexibility, if you're able to like frame it and you're helping to keep the grid online to help prevent power outages, some of them understand that and are grateful to be part of the bigger solution, but a lot of it comes down to we're helping them manage their energy costs. We're helping them to identify hot and cold points in their building and reduce those. So improving overall occupant comfort is a really big part of what we're thinking about when we're offering this solution.
Yeah, that makes a ton of sense. Okay, so I'm going to jump again and then I'm hoping I can hold just a couple of minutes because we do have some good questions in the Q&A, and I'm going to try and hold a few minutes. So we have about 10 minutes left in our session. Okay, so grid interactive efficient buildings. This topic has been featured in the Smart Buildings Exchange, I think, for 3 years. And this is our 4th year. So obviously it's an important topic. And the US DOE, as we all know, or maybe we don't all know, but now you do, has produced a roadmap document to guide market development of the technology. And yet GEBs is still quote unquote new in the market, and it's conditioned on some really different relationships between energy service providers and customers. Given the incredible complexity and fragmentation, and certainly its regulatory structure of the US utility system, what makes you most hopeful that GEBs will quickly mature as a market in the commercial and institutional space? We're going to start with you, Courtney, and then go to you, Tanya.
Yeah, I think, I mean, in the recent kind of 6 months, there's been a pretty dramatic shift. Like when we started EDO and we launched in 2021, we were talking to utilities and they would be like, yeah, we're thinking about demand flexibility. We'll get there. But now the growth of data centers and the increased manufacturing and electrification of buildings and transportation, you're seeing this growth in electricity consumption and really importantly in grid peaks. And that, has extreme weather is adding on top of this growth. And utilities are scrambling, and they're scrambling also because a lot of them have decarbonization mandates now from their regulators. And so you can't ramp up a solar plant like you used to be able to ramp up a natural gas peaker plant. And so they are really starting to look at how do we just tap into demand flexibility from all angles. And so part of that for us is like commercial buildings have not participated in many demand response programs, but are more than 30% of the electricity load in the US. And so how do you tap into this really valuable source of demand flexibility? And I think that coupled with some of the technology changes that Tanya talked us through, I mean, our data gateway, similarly to Tanya's, allows us to pull data from the building. We can also write back to the controls, AMI, the advanced metering infrastructure, and be able to have close 24-hour lag meter data. There's just some technology changes that are now enabling us to work with these really complex buildings in a way that used to take days or weeks to understand them. Now we can map them quicker. We can work with their control systems, just making all this more efficient, both in terms of cost and time.
Everything Courtney said, just like 100%. And then, from the utility side, I don't know if DERMS and ADMS are dead yet, but I sure as heck hope they're on their way. I think I used to work on microgrids a lot and then VPPs. And I did say recently, before I started my company, before I knew what I was going to do, and probably half the people on your call are going to leave after I say this, and they're going to like send hate mail to you. So I'm sorry, Carrie. Carrie's great. It's not her fault. She doesn't my views don't represent my company. They don't represent anyone here. But this is just me personally. I literally got to the point where I'm like, if I never see another microgrid again, as long as I live, it'll be too soon. Like after doing 7 of them, I'm like, I hate this. Let me just, and people would come to me and be like, can you be a consultant? I'm like, no, I'm running this company now. And let me just cut to the chase. Your HVAC load, once electrified, is going to be too big to back up with a battery. You better just control it. Figure out how to build a passive building that uses very little heating and cooling, and then make sure your heating and cooling is efficient, and then have good controls. Please, I don't want to talk to you about your microgrid. Like, I'm done. Like, I just want to cut to the important part. So I think, and then there's this idea then that if the thing that you need to control is HVAC, this idea that utilities are going to like reach into your home and control preference sensitive loads is lunacy to me. They're not, there's just so many reasons why. Like, they're not data and software companies. And if you're Tesla, you're not going to want to let people into your walled garden. You want to control the customer experience. But what utilities do have is they have that AMI meter data, and they can set rates. They can set rates. They know more than any of us know about their what the buy and sell cost of power. And I don't want to have to figure that out. You just tell me what you're willing to buy or sell energy for, and I'll figure it out on the technology side. So that gives me hope, is that I think this idea that companies that historically have never in a million years understood data governance, information technology. I mean, when I was at a utility that shall not be named, I was talking to the AMI team, and we spent $28 million to put in meters, 5-minute meter data that was just being warehoused somewhere to print out monthly bills. Like that fundamentally is not somebody who understands how to use data to make good software or decisions. And so I don't think that's what utilities should do. That's not what they're good at. They're very good at managing capital, putting steel in the ground, and they understand the economics of generating and wheeling power. And that's what they should trade in and let us do the rest. And I think that they're, at least in the more sophisticated markets, I do think that people are coming to that realization.
Okay. Well, on that, we've got a bunch of questions here. We've answered some of them. You've answered some of them. Okay, both of you talked a bit about batteries. We had a question early on. Answer if you feel you can. What does the near future for on-site or utility batteries look like? Do we expect to see an improvement to cost or materials soon? Tanya, do you want to go first or?
No idea.
Okay. Anything on that, Courtney?
Not from a utility perspective. I think from a customer perspective, we're going to continue to see the growth of batteries, and whether it's residential that are trying to deal with the new net metering rules, things like that, or businesses that are trying to make sure their businesses stay online, but from a utilities perspective. Also.
Okay. Okay, cool. Okay, another question from the audience. Buying and selling back power might be a burden on low-income housing dwellers. Are there plans to allow for them to have access to the same level of energy availability as those that are on a higher income level? Any ideas there?
I know there are companies that are working on stuff like this. For us, we couldn't get the economics to work. And I feel like they're okay alternatives. Like, honestly, a Nest or something like that is, if they can figure out how to trade the energy, and probably there are people who are working on this. I know there's a company called Universal Devices that does like residential homes, and they were in the same pilot as us with SCE. I don't know anything about their product. I don't know anything about their results. We couldn't, for our software, specifically for complex buildings that have complex physics where you can't solve it with a statistical model. So that's really that 30% of commercial buildings, and potentially in the future, I don't know, maybe industrial. So I don't have an answer to that. My guess would be that what's on the market right now is good enough. And if we can get more of those smart thermostats, like I think in some states, you actually have to have a communicating thermostat in new construction or large renovation. Like California Title 24 requires that your thermostat can communicate with the grid. I think that's good enough.
Anything to add, Courtney?
No.
Okay. Okay. Another question related to IRA. So shouldn't these first costs also be eligible to take advantage of the IRA tax credits or incentives, given that what we're doing here is sort of like a virtual power plant?
I don't know how to answer this.
I mean, I think for us, so the first part of our program is this energy efficiency piece. We're very much focused on low and no cost energy efficiency improvements. So it's broken dampers, broken sensors, broken thermostats, scheduling 24/7 scheduling when the building's only operating 8 hours a day. And so that's our core, is how do we do this without those capital upgrades? We can also identify those and kind of point customers in the right direction. But at least for EDO, it really is focused on those like low cost, quick to implement energy efficiency upgrades.
Okay. Oh, did you want to say something, Tanya? Because I'm about to
Oh,
close
I mean,
it.
we are looking at stuff like that, but I think the first order of business is having a product that can scale. Because those credits, whether it's a utility price, an incentive, or a VPP, it's like, that's nice to defray, but more and more the way that they're designing those. And again, this comes back to regulatory and working with our regulators and utilities to understand what the incentive is for the customer. They're not necessarily paying for that upfront cost. So you still have that barrier. So, if you can use it as a way to help a financier or help the customer pay down that first cost, right. And then, use it as a way to buy down the operating cost so that you're making more of a profit as an operator and can subsidize your customer's install, no matter how small. I think then it could be useful, but I find a lot of that stuff doesn't really work very well until you're at a certain scale where you can really leverage it.
Mhm. Yeah, that makes a ton of sense. Okay, well, we're at time. It's been really awesome having this conversation with you guys and hearing more about specifically what's been going on in the field. Thank you to both of you for joining us for the Smart Buildings Exchange, and thank you to the audience for participating today. We will be adjourning now for a lunch break, and the conference will resume at 1 p.m. Thanks.
Yay. Thank you, everybody. Bye.
Bye.